Hello guys. This is our second interview in the series of interview with LIGO India and its scientists in the wake of upcoming O4 run. So today we have got Professor KG Arun from Chennai Mathematical Institute, and I am Avigyan from 137 Inverse, the Physics Club of Aizer Berhampur. I am the core committee member, and I have also got my colleagues Shubharti Paul and Avijit from 137 Inverse. They are also the core committee members. So they will conduct this interview. Over to them.
Yes. Professor Arun, as you currently work at the Chennai Mathematical Institute and are one of the India's leading researchers in gravitational wave astronomy, please share with us the insights of your fascinating journey and what sparked your interest in this area.
Thank you so much for for contacting me and conducting this interview. Yeah, so it is. So I started to work in this area starting from my PhD days. So I did my PhD at the Raman Research Institute, working with Professor Bala here, and that is the first time I got exposed to gravitational waves. And during my PhD, I was mostly working on what is called a theoretical modeling or source modeling of compact binaries. So these are binaries consisting of black holes or neutron stars, and which we have seen several of them over the past observing that. So the idea would be to calculate the waveforms that these signals, how the signals look like. So that's what I did for most of my, during my PhD times. And that was my first exposure. And then since then, I think during my postdoc, I also got involved into some of the data analysis related issues, especially with the transient gravitational waves, burst, what is called a burst. And I continued to work on the theoretical aspects then. And then I did my second postdoc also. I continued to work on theoretical modeling and how we could use them to, to carry out tests of general theory of relativity. Then I joined the CMI in 2010, and since then, and a few years after, I've been involved again with the LIGO scientific collaboration, and I've been part of the discoveries and the various interesting things which followed since then. That's my quick recap of my timeline.
So your PhD was in modeling compact binaries, and how precisely do you do this? Like in terms of physics, how does it contribute to the understanding of the fundamental laws of nature, particularly Einstein's laws? Check.
Yeah, so I think the important point about the source modeling is that it is a very crucial ingredient for data analysis. So we make the best use of the fact that our existing knowledge or the prior knowledge about the signals immensely help in the data analysis of the signal. So that is why we need the theoretical modeling. Now, in terms of the physics, you can imagine that we are looking into two black holes and neutron stars orbiting around each other. And in spiral, as they lose energy due to gravitational waves, is described by some theory of gravity. That means there is an interaction, gravitational interaction between them, which is what is driving this in spiral, and eventually they merge. Now, the physics is really that this could be neutron stars or black holes which has got mass and spin and so on. So you need to have a complete description of the gravitational dynamics of these two objects, accounting for all the physical effects such as mass, spin, etc. So that is what we essentially do. But the important thing to keep in mind is that if you, for the same binary system with masses, let's say M1 and M2, the signal or the dynamics will be different in a different theory of gravity, because the gravitational interaction between them is different in a different theory other than GR. So that is where it is also linked to our ability to test GR, because if the signal we have observed is not consistent with what is expected of GR, then that is something evidence for the fact that there is a probable violation of GR. So that is why the waveform modeling or the source modeling comes at the interface of both data analysis as well as fundamental physics, because it can also be used to test whether GR is indeed the correct theory of gravity, or how close does the data or the signal match with the predictions of general theory of relativity. So that's the quick one.
The testing of general relativity and other gravitational theories is another focus of your research. So how precisely is this accomplished, and how would you describe this to an undergraduate student majoring physics like students like us?
Yeah, so I think as I mentioned, what we are really testing is that the gravitational interaction between these two objects which are in spiraling, whether that is indeed whether it obeys general theory of relativity or there is some beyond Einstein or beyond GR effect. That's what we are really testing, right? If we had an alternative to GR, so just like GR, how we are doing waveform modeling and so on, if we had very accurate waveforms in a different theory of gravity, it is simple because we could use that waveform and compare with the data and ask the question whether the signal in the data, is it more consistent with GR or with the other theory of gravity, whatever that other theory is. But unfortunately, we are not in a situation where we have a very accurate waveform that could be used for data analysis in the other theory of gravity or any other theory of gravity. So what we do instead is that we ask the question whether, so we can introduce, so there are expectations about what kind of physics could be leading to violations of GR. So what we do is that we look around GR, so we introduce free parameters or deformation parameters. So we are deforming GR and ask for whether these deformation parameters, which are like, extra parameters, which is not in GR, but will be there in other theories of gravity. But these free parameters should be taking 0 because we are deforming about 0. It's like we are just slightly disturbing GR. So the deformation parameters should take value 0 in GR, but in a different theory, it will be non-zero. So what we ask is that by introducing these so-called deformation parameters, we ask whether these deformation parameters are indeed consistent with 0, which is GR or not. So in that way, even without knowing the details of the other theory of gravity, we are still able to test GR by using our best understanding of the dynamics, dynamics in GR. So that is, we make the best use of our GR understanding and ask whether there is any deviation from GR. So that is the approach we take in all these, most of the LIGO works that we do, and it has been largely successful. We can put, so it can happen that some of the so-called deformation parameters may have, there may be other theories of gravity which may predict them to be of some finite value. So we can translate these limits or these bounds we get from the data to those theory, and we can ask how well that theory is bounded, for example. So this is the approach we take without relying on details of other theories of gravity. We test around GR and we test GR is correct or not. That's a question we ask instead of asking a more general and more general question of whether something else is true or not. And of course, once we detect some violation of GR, we have to think about what that violation is and how we can understand them and so on. But that'll be a level 2 question after identifying or after having seen some very confident signatures of violation of GR.
So Einstein's general relativity plays a major role in your research.
Yes.
So the connection between short gamma ray bursts and gravitational waves is another current research interest of yours. So how can LIGO or maybe LIGO India in the future be of a long-term assistance in this regard? And will O4 run be able to be any assistance to you or your research?
Yeah. So I think, the gamma ray burst is an electromagnetic phenomena. We are seeing jetted emissions from some, of some source. We don't know what that is. But astrophysicists, people have conjectured already that, the short version, one class of this gamma ray burst could be coming from mergers of neutron stars or neutron star and black hole, wherever neutron star is involved. And this was, of course, confirmed by our Dijkstra binary neutron star signal in 2017. We saw a gravitational wave and a gamma ray burst together, and we now know that at least one class of these mergers does happen. So that is where it is coming from. Now, the question that we want to ask is that, of course, we knew this gamma ray burst for a long time, decades, for example. But why gravitational wave is important is because of the following. So this gamma ray burst, is the emission, whatever that is coming up, is coming much farther away from the source. So we are not able to probe the physics close to the source. So if it is due to the merger of two neutron stars, there is some remnant formed, and the remnant is doing something to give out the jet. But what exactly this object is doing to give a jet, which happens much later, we cannot probe that regime because electromagnetic emission happens much later and much farther from the source. So that is where we need to, if we have gravitational waves, because we are seeing the three phases, the early in spiral, then they come closer, they merge, and then there is a new remnant that is giving you probably the jet, right? So this is what gravitational waves can tell you, that the jet, the details of the jet and how the jet is related to the central engine. Central engine is something which is launching this jet. which should be a remnant of the merger. And what kind of jet is it launching? Is it what is the geometry of the jet? For example, we can see a jet only when it is launched towards you, because a very narrow jet, like a conical jet. So if you are viewing it off axis, that means you are not viewing exactly along the axis of the cone, you may see different structures and so on. So geometry of the jet and the structure of the jet. For example, we do not know how does different layers of the jet composed of and what is the details of that. So these are things which are related to central engine, which the electromagnetic observations alone cannot completely probe. So what gravitational waves will enable you is to combine the information from gravitational waves and the electromagnetic observation, and together they should give you a more complete picture about what is the central engine and what is the source that we are seeing, what is the structure of the jet, and what is the geometry of the jet and so on. So that is why it is very important to combine. That's why the relevance of combining electromagnetic and gravitational waves, and that's called multi-messenger, because electromagnetic wave is one messenger and gravitational wave is another messenger. So it is important to combine, you get a more coherent and more synergetic a combination of the thing. So that's one thing. Now coming back to LIGO, what is important to identify a gamma ray burst in association with the binary neutron star merger is that we should be able to localize these mergers, whatever is happening, to very good accuracy. Only then one can point electromagnetic optical telescope or gamma ray telescope and so on to that patch of the sky to detect a gamma ray burst, right? So this, usually our existing network of detectors are not very good in source localizing. It may have hundreds of square degrees error bar in the sky. It's very huge. So one cannot expect electromagnetic telescope to follow up such a huge patch of the sky. However, once you have a global network, including LIGO India, for example, which is very well separated from LIGO and Virgo on other continents, we expect that our ability to localize these sources should dramatically improve, which should mean that our ability to follow up on gravitational wave mergers to look for gamma ray bursts should also dramatically improve. And that is why, LIGO India, once it realizes, should significantly impact our multi-messenger astrophysics that LIGO and Virgo and LIGO India can do together. So that is where the LIGO India aspects come, because we have a geographically separated detector, which is like a larger baseline, and hence we have a significantly improved source localization, which in turn helps all the physics I mentioned in the beginning. So that's where the LIGO India would play a very important role in the gamma ray.
So now please provide more details about how you helped the LSC. You participated in the discoveries made during the earlier LIGO runs, which produced some stunning findings. So could you briefly describe your involvement in the prior observing runs like O3?
Yeah, correct. So I think not just O3. So I think, as I told you, I'm involved in the LSC from 2012. Whenever the Indigo, the Indian group of LIGO LSC was formed, we have been contributing, and of course, we happen to be also part of the first discovery, which won the Nobel Prize in 2017 and so on. So, but my contribution has been mostly on the test of GR side. So basically, fundamental physics using gravitational waves, and to the detection and the following thing, we contributed to different analysis which allowed us to test GR by various means. So I told you about generally how it is done, but specifically we can do it in various methods, because we want confidence and we want to try various aspects, various predictions of GR. We want to test them to see whether that is indeed holding true in the data. So I was involved in developing, for example, a test of propagation of gravitational waves. So this is when you have gravitational waves according to GR will propagate non-dispersively. That means there is no dispersion. Different frequency components of the wave will travel with the same speed. So one can use the data and ask the question whether there is any evidence for non-dispersive propagation of gravitational waves. And if we see some evidence, it will mean that GR is not the true theory of gravity. So I was involved in the developing a method with a former ICER Kolkata student, Anuradha Samajhdar. So we contributed with other collaborators, of course, a method which is now part of the usual LIGO, all the test of GR that LIGO does, which is to constrain possible dispersion of gravitational waves. So that is one of the things which is now kept. We keep doing it in all the future observing runs. The other thing which I was involved in is with a former student of mine, Krishnendu. So we developed a method to test whether these mergers that are happening. So what are binary black holes? So there is also scope for black hole mimickers. So these are objects, compact objects, which are not quite black holes. They mimic or they fake the properties of black hole, and hence it is very difficult to distinguish them from black hole. This kind of candidate objects can exist from theoretically. So we wanted to ask the question that how we can use gravitational observations to constrain whether these are indeed mergers of binary black holes or some of these exotic alternatives to black holes. So we developed a method which uses spin-induced multiple moment. This is a technical thing, don't worry about it. We use spin effect as a way of gauging whether these objects which are merging are indeed black holes or not. So this was developed by, we developed it, we contributed to LSC, and this is again now part of the standard type of test we do. So this is another thing that I was involved in. On top of it, I've been contributing to different small things like analysis, reviews, and so on. But now specific to O3, I also happen to be so usually the LIGO scientific collaboration will form a editorial team which is in charge of writing the paper, this collaboration paper. So I happen to be the chair of the editorial team which led the test of GR paper, the paper which reported several types of tests of GR using the O3B, the previous observing run. So so that means I help to write the paper, coordinate different analysis, make sure things are all fine and so on. So that was something which I contributed towards the O3B as well as the O3B. And as I mentioned, all the analysis which I mentioned are now applied regularly on all the observing runs and also the future one. Now, right now, I'm also working with a PhD student of mine, Sayantri Datta, to improve the efficiency of some of the tests that is done. So that we want to use methods such as data-driven methods such as singular value decomposition and so on to optimize the existing tests of GR. So we are developing some of these things, gearing up for O4 in mind, and hopefully we can add that additional layer, and optimize some of the things to do a more rigorous and robust test of GR. So that's a rough idea about what I will go through.
So basically, the O3 run was extremely successful.
Yeah.
So what exactly do you expect from the O4 run in general? Not in your field only, but in general.
Yeah. So I think, what is impressive about O3 is that O3 has seen very diverse kind of sources. So for example, now we have seen a binary black hole. We have seen several binary black hole mergers, at least one binary neutron star, at least two binary neutron star mergers, and at least one neutron star black hole merger. This completes all the compact binary thing. Right? And also, if you look into the details of binary black holes, we have seen things with very asymmetric systems, very mass ratio, M1 by M2, mass ratio of close to 10. We have seen very high mass merger, almost like intermediate mass black hole, like 150 solar mass. We have also seen a highly precessing system, that is, when the spins of the black holes are not aligned with respect to orbital angular momentum, it can do a larger kind of precision. So we have seen them. So we have seen many, already we have seen many diverse types of binary black holes, apart from binary neutron star and neutron star black hole. So I would expect that this diversity is going to again increase, because we are going to see hundreds of them during O4. So we would be seeing much more diverse and many surprises, because we need to, we didn't know about the existence of many of these things until we detected them. So I'm sure we are going to be thrown, we'll be having many surprise discoveries in O4. So if you ask about my wish list, I think I would say that, one binary with an orbital eccentricity. So what we have seen so far are mostly binaries which are close to the merger. They are in circular orbit because they move on circular orbit. So it can happen that some of the formation channels, so some of the ways in these binary black holes may form, it may lead you to some eccentricity by the time they merge, or very close to the time we observe them. So it is going to be a very interesting thing, because it can tell you something about the formation channel. So definitely a binary with eccentricity will be something which I would like to see. And other thing is, of course, that we saw one binary neutron star merger with their electromagnetic counterpart in the 2017. But we have not seen any neutron star black hole mergers with a short GRB counterpart. So it'll be great if we detect one neutron star black hole merger with a GRB. And also, maybe Ajit already talked about it in his thing. So lensed binary black holes. So these are like binary black holes, two copies of the same merger coming at with this kind of delay. It will be another exciting thing, because it is going to tell us about structures that is there in the intervening space between the source and us. So these three, that is eccentric binary and multi-messenger neutron star black hole merger and the lensed BBHS would be my three wish list. Three of the top wish list for me for all.
India is also constructing the LIGO detector, which is billed as a fantastic initiative for fundamental research. So, what impact do you think it will have on the GW astronomy discipline, and how will it help to raise awareness of fundamental physics?
Yeah, so I think the important thing about LIGO India, once it's realized, it's a very complex instrument. We know that LIGO is a very complex instrument. So once we install LIGO India and run LIGO India, we would have demonstrated that we can build and manage and run this complex instrument, which of course a big inspiration for all those who wants to work in experimental gravity and gravitational waves and so on. So that's of course is going to be a great thing for us to achieve. I already mentioned about the implications for it in the case of GRBs and so on. Now, in terms of community, so one would expect by the time LIGO India is realized, we would have a much wider community which works on theoretical aspects, data analysis aspects, and experimental aspects. It would mean that, and of course, gravitational waves is a really new field of astronomy. It is yet to give you many, many surprising elements of the universe. And so we are going to discuss many, many interesting and exciting discoveries in the coming years. So it is a very interesting area that younger people would like to get onto in any of these aspects, as I told you, theory, data analysis, or experiment. But with the LIGO India being realized and we building a community which spans across these disciplines and spread over India, I think it is going to be extremely important that, if a younger student want to get into the thing, I'm sure he or she will find enough people to interact initially and do a internship, for example, and get trained and contribute to these efforts. Because this is going to be, we are just at the beginning of a new era in astronomy and there is a lot for it to see. So I'm sure that in terms of the people getting into, it is going to be very important. Of course, that will also mean that as a community, basically senior people and PhD students working in this field, they should all be on watch out and make people aware of the excitement about this new field and what to expect in the coming years and why it is exciting and so on. So I think overall, LIGO India and the community that LIGO India will develop along with its installation and running and so on is going to impact the Indian astronomy and the Indian physics community in a very big way. I would think that's my take on.
So just a question, just my curiosity. You talked about, while talking about gamma ray bursts, you said that we cannot detect the gamma ray bursts that are away from it, that are directed away from us. So actually we cannot detect it, or there are some methods to detect it?
So I think what happens, the gamma ray burst, we can detect them. I'm talking about electromagnetically, because electromagnetically, so this is a very narrow beam of like a jet, and the jet opening angle is like, it may be 10 degrees or something like that. So we can detect them only if it is pointed towards us. So we will miss a lot of GRBs which are pointed away from us, but then the number of such events in the universe is so high that a subset of them will always be pointing towards us. So we will be missing anyway using electromagnetic telescopes, but we will see still a pool of GRBs. But if you look into gravitational waves, because gravitational waves are not, it's not pointed detectors, so gravitational waves wouldn't care whether there is pointing towards us or not. That is why the second binary neutron star detection, the one which happened in 2019, we did not see any electromagnetic counterpart. But we did, it may be that it also gave you a jet, but that jet was away from us or was fainted from us. So, but gravitational waves is not so sensitive to this beaming aspect, but electromagnetic telescopes are sensitive to it, and it can see only if you lie within the cone or slightly away from the cone and so on. So we will be missing many of them, but then the number is so high that we will still see a subset of them in any case, even if they are pointed away from us.
So basically, this gravitational wave detection acts as a fail-safe. Even if we don't measure the electromagnetic thing, we can measure the gravitational wave from
exactly. So I think we can see binary neutron star merger happened or a neutron star black hole merger happened, but but whether it produced a gamma ray burst or not, we cannot tell. Ideally, but definitely the mergers we are seeing, regardless of whether there's a GRB accompanying or not.
Okay, so that's all that we had for you, basically. So thank you for answering all our questions patiently and helping us get more information about this and making us more interested in this field.
Yeah, thank you so much. So I think it is great, and thank you so much for your time in placing these questions and so on. Thank you so much.
And, yeah, thank you, sir. Thank you.
Okay, then. Bye bye.
Yes, sir.
Thank
bye.
you very much
Bye.
for connecting with us.